Hi guys, this is Tavish from Differential Equations. I hope you guys are doing well and I hope your studying for midterm 2 is going well. Today I wanted to show you guys a trick that I use to find the eigenvalues of matrices that I think is faster than some of the ways that we've learned to do it in class. So to start, let's just start out with some simple matrix. Let's call it matrix A. And sorry if my handwriting is kind of bad. I don't really have a tablet or stylus, so I'm kind of just doing this with my trackpad. But so here we have matrix A, and we know that matrix A is going to have two eigenvalues because it's a 2 by 2 matrix. And to find these, the way that a lot of you are probably doing right now is to take A and find the determinant of A minus lambda I. And this method works really well and it's super reliable and it'll like save you in pretty much any situation. And if we did this, we'd get 1 minus lambda 2. That's an interesting 2. 1 minus lambda. And then we'd find the determinant of that. So that would just be 1 minus lambda squared, since we take the product of these two minus the product of those two. And then we can subtract 4, because it's minus 4, and set that equal to 0. And from this, it's actually not that bad. For this particular matrix, we can just find the eigenvalues really easily from this quadratic equation. But there might be some matrices where it's not so clean and dry, and where the quadratic equations might take a bit more thought or a bit more factoring. And even for this one, it still takes a second or two to do this. So what if I told you there was an even quicker way to find eigenvalues? Let's take a look at what we can do. And I'll keep that version up so you can compare them as we go. But something that I do to find eigenvalues, one thing that you can do is turn it into a triangular matrix where all the values either above or below the diagonal are 0. And that also works just fine. But again, if we have matrices with like crazy values, which we'll look at in a little bit, that might not be as easy to do quickly. But there is something that I do that does work for most matrices as long as the numbers are nice and not crazy, which most of the matrices we've been looking at are. What I do is basically I look at the diagonal of this matrix and figure out the sum of the diagonal. So for these two, it would just be 1 plus 1. So the sum, let's just call it S, equals 1. And then I look at the determinant of this matrix. So the determinant of this oh no, sorry, the sum is not 1, it is 2. The determinant of this matrix is kind of the same thing we did here. It'll be 1 times 1 minus 2 times 2. So that is -3. So those are our two values that we have from there. Now, to find the eigenvalues from this, we do something that's actually derived from this same formula here, the setting the determinant equal to 0. We take these two values, and this is a very intuitive way of doing it, but we have to think of two values that add to give us the sum, but multiply to give us the determinant. Now, at first, this might seem a little bit difficult to do, but practicing it a few times, I think it becomes really easy, and you can see the answers almost instantly as you start to use it. So just looking at this, I think of two values that add to 2 and two values that multiply to give us -3. Well, we know that since it's negative and we only have two values, one of them has to be negative to multiply to a negative number. But since the sum is positive, the negative number's magnitude has to be smaller than the positive number's magnitude. Now, you won't always have to go through that thought process, but it's just a good way to clarify that. So looking at that, I think that two values that would work are 3 and -1, because 3 minus 1 is 2, and 3 times -1 is -3. Yeah, so that's the shortcut. Now let's look at this for a matrix that wouldn't be as easy to use the other two methods for. Let me just, oops, let's keep the A. I wonder if you guys can see my cursor. Um, let's just get rid of all this. Bam. So let's look at the matrix 12, 3, 10, 5. Yeah. Hopefully you guys don't hear my clicks too loud, but I apologize if they are. So let's apply the same method that we just used. We can see from this matrix that these might not be the nicest values to do a quadratic with or try to get into triangular form because we'd have to work with fractions. And I know a lot of people don't like to work with fractions. So let's look at this matrix. We see that the sum of the diagonal is 17. And the determinant would be 12 times 5, oops, times 5 minus 10 times 3. So that would be 60. That is a 60 minus 30. So it's just going to be 30. So we need two values that add to 17 and multiply to give us 30. And these symbols are just like, oh, that's not a 3 anymore. These symbols are just like sum and product, but yeah. So looking at these, the two values come to my mind quickly because I know that 30, the two common ones I think of are like 15 and 2, but we also have like 1, 2, 3, um, a lot of factors actually, 5, 6, 15, and 30. I might have missed one or two, but looking at the ones that add to 17, I know I can only have two positive values that add to 17. So I know real quickly that my eigenvalues would be 2 and 15, or 15 and 2. The order doesn't matter. But yeah, that is how you would use that method for this matrix. Now, there's just one more thing I want to talk about. We know that this method works for 2 by 2 matrices, but what about 3 by 3 matrices? Well, it actually does work for 3 by 3 matrices, but there's a caveat. So let's say we have like 2, 3, 1, 1, 2, 3, 1, 4, 1. So we want to find this matrix's eigenvalues. And we know that there's going to be three eigenvalues since it's a 3 by 3, whether or not some of those are repeated eigenvalues. So we have, or we need three eigenvalues for a complete set. But we know that we can do the a minus lambda I. And for a lot of things, you might want to do that because it's very reliable and it'll like always work, even if your numbers aren't the nicest. But say that we want to try using our method. So to do that, we take again the sum of the diagonals. So we just have 2 plus 2 plus 1. So our sum is going to be 5. And then our determinant is going to be just the determinant of a 3 by 3 matrix. So like it'd be 2 times 1 minus 3 times 4 minus 3 times this guy and this guy, this guy and this guy, plus 1, and yeah, and so on. So that's just that whole formula. But to save time, I've calculated it beforehand. So this matrix, oh my gosh, this matrix's determinant is actually negative 12. Okay, so looking at that, we know that we have three values. They need to add to 5 and give us, they need to multiply, they need to multiply it to give us negative 12. So this, you might see now why, you might start to see now why it's harder to do for 3 by 3. It's a bit harder to think of three values as opposed to two, because it seems like there's a lot of things that could work, and there almost are, because there's so many like groups of factors for both of these. So looking at 12, or looking at just the signs, we know that since this is negative, only one of our three values can be negative because it has one or all three. Because if the product is negative, an odd number of values has to be negative to multiply to that. And if it's positive, it's an even number, so 0 or 2. But since we see that our sum is positive, we know that only one can be negative. Um, yeah, this thought process will help like clarify it, but a lot of times you'll find that the negativity comparison isn't necessary. But looking at that, we know that we need three values and one of those values will be negative. But where do we go from here? Well, just like thinking and trying out different values, we can come up with the values 6 and 2 make 12, but so do like 3 and 4, 12 and 1. Um, yeah. But and on top of that, we need a third value. So judging by the 5 that we have here, actually, a good thing to do would be like for all of these combinations, we know that if we use two of these, our third number would be 1. Or if we have like 3, 2, and 2, because we need combinations of three numbers. For this one, though, the answer is actually something with 6 and 2, but we need to figure out which one is positive and which one's negative. Well, since we have 5, let's try 6 and negative 2. That gives us our answer, but we still only have a sum of 4, so we just need to add 1, and that'll give us 5. But without having like, it's a lot harder to do for this 3 by 3 matrix, and it gets even crazier if we have, like, 3 by 3 matrices that are, like, don't have as nice numbers, even if the numbers are just slightly off. If we have, like, 2, 3, 1, let's say 8, 2, 3, 7, 11, 2. The eigenvalues of this matrix, I don't know what they actually are, but they might not be whole. They might not be rational even. They could be like 2.221 plus square root of 47 over 13. I'm just making these up. But if your eigenvalues aren't perfectly like as we want them to be, this method won't work, especially for a 3 by 3. And a lot of times, for 3 by 3s, the A minus lambda I would be more reliable. And even if they are perfect, as you might have seen, it's a lot harder to figure out three like working values because it feels like there's so many groups that could work as opposed to a 2 by 2. But the bright side of this is that for a 2 by 2 matrix, this method is very reliable. You can always just kind of look at a matrix and be like, sum the sum of these, the determinant, and find it from there. So it'd be like 6 is the sum, and -25 is the product. I'll leave that one for you guys. But I hope this video helped. Best of luck on your midterms, and let me know if you have any questions. Thank you.